Arnaud, you can start.
Okay, thank you. So thanks for the invitation. I'm sorry I cannot be with you. So I'll be talking today about generative modeling, and in particular about a novel class of generative models that has emerged about 2 years ago, which are known as denoising diffusion models, and which have become actually very popular in the past 2 years. I will basically go through this class of models and show how we can improve them, and in particular speed them up using ideas from optimal transport. So this is joint work with a variety of colleagues, mostly from Oxford, and also some PhD students whose name can be found below. Okay, so I will just first start by basically kind of introducing the class of denoising diffusion models, the kind of rationale behind this class of techniques, and present a few theoretical results we've obtained. All right, so generative modeling, you're attending a summer school in artificial intelligence, so I guess I don't need to convince you that generative modeling is at the core of machine learning on artificial intelligence nowadays. Okay, and it's used really literally everywhere. It's used in particular, like for example, for protein, image synthesis, language modeling, and there are many more applications, I could think of, but basically I'm not going to spend time motivating the need for generative modeling because any attendant in artificial intelligence conference should know this is as the core, basically a core component of artificial intelligence. There's been massive progress essentially in this area in generative modeling over the past, I would say, 8 years. It all started maybe originally with work like the work of on variational autoencoders by Kingma and Willing, on my colleagues from DeepMind, Danilo Rezende, Shakir Mohamed and Vistra. And then basically there was also the kind of really influential work of Goodfellow on a generative adversarial network that really has become one of the most cited paper in computer science since its publication in 2014. Okay, so these methods have become extremely popular, and yet really there's been over the past 2 years a novel class of technique has appeared, which is known as score-based generative models or denoising diffusion model, and it turned out that those techniques perform extremely well, so they become really prominent in a small amount of time. Okay, so this is there's a growing literature on this topic. And there's literally almost new papers every day on arXiv. So for those of you who are interested, I have put a link to a website that has been basically developed by my PhD student postdoc, which is essentially a compilation of all the publication on this topic. Okay, so why are people really interested in the denoising diffusion model? Well, it's simple. It produces actually remarkable empirical results, and in particular, on a variety of domains, including image synthesis, audio synthesis, and so on. Those models outperform GANs, okay? And in particular, those denoising diffusion models are also at the core of the very recent developments in text-to-image models, such that DALL-E 2 that was developed by OpenAI, as well as ImageGen by Google. Okay, so this class of techniques, I'm sure you've already seen some kind of demos of these models, and it's extremely impressive. Okay, so that's a really interesting class of models. And what we're going to try to do in the first part of the talk is to understand the kind of basic ideas between denoising diffusion model. Okay, and to do that, I will start really introducing this kind of techniques using elementary concept of probability, which is a slide that could have been entitled Markov Chain 101. So bear with me for the timing. We're just going to do like to really introduce this kind of simple elementary mathematics, and I will relate that later on to the problem of generative modeling. Okay, so I'm going to give you, I'm going to define a Markov chain in discrete time, and it takes value in RD, so the state takes value in RD. And I say, well, if you want to define a Markov chain In RD, well, what could you say? Well, you're going to have to define the initial distribution of this Markov chain. Let's call it P naught. And then you're going to have to define the evolution of this Markov chain. And because our work in RD is going to be given by some kind of transition density that takes you from, say, the state at time k to the state at time k plus 1. Okay? So if you unroll this kind of simulation of the Markov chain from time 0 to time n, what you have, well, you have a sequence of states, x0, x1, x2, xn, which basically admits a joint density given by the formula written below. I use here MATLAB notation. So I have an initial distribution P naught of x0, initial state, and the product of the transition density that takes you from the state at time k to the state at time k plus 1. Okay. So I define this kind of Markov chain. Okay. And in practice, in the context of generative modeling, what we will be doing later on, I will go back to that later, is we will define a Markov chain that progressively add noise to a state x0 that was distributed, that was from the empirical distribution of my data. Okay. Okay, but for the timing, forget about that. So I define the joint distribution for a Markov chain. Okay. And from this kind of definition, I can also define the marginal distribution of xk under this Markov chain forward dynamics. And this is obviously, this marginal distribution is given by the so-called Chapman-Kolmogorov equation. And it tells you simply that what is the marginal distribution at time k of my state xk? Well, it's simply the marginal distribution at time k minus 1, which has been pushed forward through the transition at time k on an integrator of xk minus 1. Okay, so everything is just elementary mathematics. Okay, now what's going to be really important in the rest of the talk is to say, if you simulate, essentially, you want to simulate from the paths of the Markov chain from time 0 to time n, you can do a forward simulation, as I've previously described. That is, you sample at time x0 from from P naught, and then you use the transition density of your Markov chain. But what you could do alternatively is use a backward decomposition of this joint density. Okay, so what is the backward decomposition of joint density? Well, you still have a Markov chain. Okay, if you have a Markov chain, if you look forward or backward, is always a Markov chain. Okay. This backward decomposition tell you that to sample from the joint distribution of the Markov chain, we could do alternatively, you could sample first the state xn at time n, and then recurse backward according to transition kernel that takes you from time k plus 1 to time k. Okay, so you have either the forward view of your Markov chain, either the kind of backward view of the Markov chain. Okay. The backward view of the Markov chain is a kind of alternative, which is interested in our own say, as we're going to see. It basically leads to this so-called ancestral sampling procedure, so as to sample from a Markov chain path, which is I sample at time n from the marginal distribution Pn of the state xn, and then I basically recurse backward using this kind of backward Markov transition kernel that take me from time k plus 1 to time k, on which are obtained from the base rule using the forward transition kernel. And I'm going to do the maths later on. Okay, so very elementary basic probability on why is that relevant to generative modeling. So what I'm telling you why it's relevant to generative modeling is that the key idea between this denoising the diffusion model is going to be as follows. It's going to be where what I'm going to do is P naught is going to represent essentially the empirical distribution of the data I have access to. So if, for example, you have access to CIFAR10, okay, so that's going to be empirical distribution of the database of images, okay. And what you're going to do, you're going to define a Markov chain which is going to add noise progressively to this data, okay. So that's what we're going to do. So for example, this is what is represented at the top of my slide. You could have sampled from your database of images an image of a dog, and then you define some kind of forward transition kernel that basically progressively transform this image into a Gaussian noise sample. Okay, that's the forward dynamic. And what we're going to do, we're going to try to essentially invert this dynamic. We're going to say, well, it's very easy to go from, say, an image sample to a Gaussian noise sample, but well, if we could kind of reverse this kind of forward dynamic, it means that we could go back from using ancestral sampling from Gaussian noise sample to a sample of an image at time 0. So that's really the key idea that is behind those denoising diffusion model. Okay, so really the setup we're going to always assume in this in the rest of this talk, although there'll be exception a bit later on, is that P naught is going to be this kind of empirical distribution of the data, and you define some kind of forward dynamic so that the marginal distribution of your sample basically at time n is going to be roughly typically Gaussian. So I'm going to call it PRF, but typically it's going to be a Gaussian distribution. Okay. So, and it's very easy to build a Markov chain that does that. So what you could do, simply you could put some forward transition kernel where some kind of autoregressive Gaussian process, and you know that if you do that, and if alpha here is strictly inferior to 1, say 0.99, then really, because of the mixing property of this kind of autoregressive Gaussian sample, whatever being the initial state of the Markov chain, after a while, you're going to have a sample this is roughly Gaussian. Okay, so that's really the idea. So you go from, say, an image to a Gaussian noise sample, and now really the rationale is to say, well, generative modeling is trying to do the reverse thing, which is going to be to go from essentially a Gaussian noise sample to something that looks like a sample from P naught. Okay. So to do that, we're going to try to mimic what ancestral sampling does. That is what we like to do is at time n, we would like to sample for the marginal distribution of the Markov chain Pn. We can already do that, but because we know that really essentially we've built our forward dynamics so that the marginal distribution at time n is roughly a Gaussian when we replace Pn by a Gaussian noise sample, and then we would like essentially to simulate from this kind of backward Markov transition kernel to get back to get at time 0 a sample that looks like a Gaussian noise sample. Okay. So I give you another illustration here that is taken from an excellent paper of Song, who got the best paper award at iClear in 2021. So here, this is a very, very simple example where the distribution of the data would be simply a kind of bimodal Gaussian distribution. And essentially what you do, you define a forward, essentially dynamic that transforms this kind of distribution as some kind of Gaussian distribution. And what ancestral sampling does is that it reserves this mechanism, and basically you want to generate for ancestral samplings something that's going to basically turn Gaussian noise sample as sample from the initial, say, data distribution P naught. In this case, a mixture of two Gaussian distributions. Okay, so that's really the core idea behind this kind of denoising diffusion model. Now we have a few problems to implement this, because the question is, well, okay, how do we essentially sample from this kind of backward Markov transition kernel? Okay, so we need to look at that a bit more carefully to see how it is possible to sample from this backward Markov transition kernel. It's very easy to sample from the forward Markov transition kernel because there are simply some kind of this kind of autoregressive Gaussian kernel, but the backward Markov transition kernel is quite unclear what their structure is. Okay, so let's have a look at those kernel. Basically, what we're going to use to start with is very simple. So we're going to remember that really we use transition kernel, forward transition kernel, which are autoregressive Gaussian, where alpha is something that's going to be close to 1, say 0.99, because we really want to add noise progressively to our data, but really it has to be kind of really gradually and quite slowly. Okay. And then we say, well, what is the expression of the backward Markov transition kernel? Well, the backward Markov transition kernel is just given essentially by the base rule. So what it is, it's essentially the forward transition kernel multiplied by pk of pk plus 1, where pk is, remember, is the marginal distribution of the state xk under the forward dynamic. Okay? So here, the first expression I give for the expression of the backward Markov transition kernel is exact. And now what we're going to do, we're going to try to approximate this expression. Okay. So what we're going to do is something that's going to be kind of looks like a bit dirty mathematics, but we will make that a bit more rigorous later on. And it's to say really that because I've assumed that essentially my Markov transition kernel move my sample kind of very slowly, okay? So somehow pk is approximately equal to pk plus 1, okay? There's not much difference between the marginal distribution at time k and at time k plus 1. And what I'm going to do then is I'm just going to essentially do some kind of Taylor expansion of, so I'm going to replace pk of xk by pk plus 1 xk, and then I'm doing a Taylor expansion of basically this quantity, and I end up essentially with this expression here. So what I have now, I've rewritten my backward Markov transition kernel as an expression which is a kind of simple expression because it tells me that this is a Gaussian distribution of argument xk on a mean that is given by this expression here on a variance covariance matrix which is proportional to the identity. Okay, so what we've done is that we had an intractable backward Markov transition kernel, and now we've shown that it's essentially some kind of Gaussian transition kernel, but it still depends from an intractable quantity. And this intractable quantity is the so-called score or Stein score. So this is the derivative of the log of the marginal distribution under the forward dynamic, and the derivative of the C being respect to the spatial component x. Okay, there's no hyperparameter here, theta. Okay, so don't mix that with the score, like what we call the score in statistics. It's not, has nothing to do with the gradient of the log likelihood. Here, this is the Stein score. This is a gradient with respect to the spatial derivative x. Okay, so this quantity once more is intractable. So it doesn't seem that we've made much progress. But what we're going to do here is leverage the structure of the transition kernel, or the forward Markov transition kernel. So what do we know? Well, we know that basically I can rewrite this kind of Markov, this kind of marginal distribution xk plus 1 as simply the initial distribution p naught x naught, that is the data distribution, and where I multiply that by the transition that takes me from x naught to xk plus 1, and I integrate over x naught. Okay, so this is elementary Markov calculation, probability calculation once more. And here there's something which is quite useful, okay, that we're going to exploit, which is that because we have a very, very simple forward dynamic, it's just given by this autoregressive Gaussian process, I do have access to closed form expression for the Markov transition kernel that takes me from x naught to xk plus 1. In part, so this transition that takes me from x naught to xk plus 1 is available analytically. It's a simple Gaussian distribution. Okay. So what I do now, when I've got essentially some kind of Sanova-Chapman-Kolmogorov type equation, well, by elementary calculation, if you take the log onto the gradient on both sides, yeah, you're going to end up that you can rewrite as follows. So the gradient of the log of the marginal, that is the score I'm interested in, okay? Well, what it is, so it's going to be an expectation, and I'm not going to specify yet what, with respect to which distribution, but it's the expectation of an integrand, which I know, because this is the gradient of the log transition, which is available analytically. And here, this is with respect to the distribution of x naught given xk plus 1. Okay, so I have basically rewritten this kind of intractable quantity as this actually the expectation of a quantity I know exactly, but this is with respect to distribution, the distribution of x naught given xk plus 1, which is still intractable. Okay, but yet we've made progress, because essentially what we've done is that we've replaced the intractable quantity by some kind of conditional expectation. Okay. Now, that suggests a way to approximate this quantity, which is to say, well, because the score is this conditional expectation, it can be essentially reformulated as the solution essentially to a regression problem. So if I had access to all regression function, measurable function S of xk plus 1, and if I were minimizing the expectation of the square difference, okay, between S and the gradient of the log of the transition square, so we are minimizing that over all possible essentially measurable function, what I would have obtained is simply the conditional expectation, by definition of conditional expectation. We know that the conditional expectation is basically the quantity minimizing this type of minimization problem. Okay, so in practice, I don't have access, obviously, to all measurable function, but what I'm going to do basically is I'm going to replace that by some kind of neural network and minimize over the class of neural network. Okay, and importantly here, the expectation is not anymore with respect to the conditional distribution of x naught given xk plus 1, but this is with respect to the distribution of x naught and xk plus 1. On what is the distribution of x naught and xk plus 1? Well, this is something I can very easily sample from, because what I do to sample from the joint distribution of x naught and xk plus 1, I pick a sample in my database of image, and I add noise to it, and here we go. I've got a sample from the joint distribution. Okay? So that's the way you can estimate essentially the score of this, essentially, this intractable score is by solving some kind of regression problem. Okay. So now you need to evaluate, because we want not only to evaluate basically the Markov, this is the kind of backward Markov transition kernel at a given time step, but over all the time between 0 and n. What we have to do, we have to estimate the score of all the marginal distribution, P1, P2, P3, P4, Pn, and so on and so forth. And instead of basically having one single different neural network to approximate each of the score, we use one single neural net. We give it two input, time and space, and we minimize essentially all this kind of square error. And this is the way basically we're achieving, we're going to learn the score using one neural net, okay? And obviously, the way it is done is by mini batching, essentially subsampling over the time index here, on mini batching on using stochastic gradient, okay? So that's kind of very simple. And once we've done that, well, we kind of done. So we basically use some kind of corrupted version of the data so as to learn the score of the actually basically the distribution of noisy data, and then we mimic ancestral sampling. Now, so mimicking ancestral sampling, it tells me you sample at time n a Gaussian noise sample, and then you sample from the approximate backward Markov transition kernel, which is given by this expression, and at time 0 you obtain essentially a sample which is approximately from the distribution of the data. So this is really this kind of idea which is at the core of all this kind of denoising diffusion model on score-based generative model. Okay, so it's a very, very kind of simple idea, and you can find a lot of code available online. Okay, so that's the kind of the way it's presented in a kind of quite a bit of the literature. So why is it called diffusion? Well, it's called diffusion because really it's perhaps more elegant to think of this procedure in continuous time. Okay, so remember the kind of process we use so as to kind of perturb the data in a forward path. We use this kind of autoregressive Gaussian process, where what it is really is nothing but some kind of time discretization of a so-called Ornstein-Uhlenbeck diffusion. Okay, so really maybe better to think of it in continuous time. Really, you add noise using the kind of continuous time process really. And if you were to time discretize this diffusion, you obtain a process as described previously in my slides. Okay. Now, so you think of it, what this equation, the first equation that is on my slide here, what it represents is really represent the kind of forward view of the Markov chain, where you sample X naught according to the distribution P naught, the distribution of the data, and you corrupt it progressively using some kind of essentially Gaussian noise, okay? And you know that the equilibrium distribution of such diffusion is essentially a multivariate normal distribution. Okay. Now, what is the equivalent of this kind of ancestral sampling procedure when you think of basically of diffusion process? Well, you can think of it as looking at, if you look at my diffusion process forward, so it's 0 to time t, well, you can also look at this continuous time process in a backward direction, time reverse direction. So I define this time reversal process. On this time reversal process, it has been shown by probabilists that it is also a diffusion. Okay, it's also a diffusion process. And it's a diffusion process whose drift is actually dependent on the intractable score of basically the diffusion of the forward process. So you can think of the second equation as basically circular, as exactly the equivalent of ancestral sampling in continuous time. So that would be the exact ancestral sampling procedure, okay? There's two sources of intractability, to simulate such diffusion. First, there's the fact that we do not have access to the marginal distribution PT of the forward diffusion at time t. And also the second thing is that we do not have access to the intractable score of the forward diffusion. So when you do this kind of generative model, you make two approximations. The first one is you say, well, you know, if my diffusion has relaxed enough, PT is approximately a Gaussian, so I replace PT by some kind of Gaussian distribution, and then I replace the intractable score by some kind of neural net approximation, which has been basically selected so as to minimize some kind of error. So in the previously, the way I presented it was by saying, well, you can think of it that the score satisfy the solution to some kind of regression problem, and I solved this regression problem approximately using neural network. Alternatively, you could say, well, what I do is that I pick the kind of, in continuous time, I think of this kind of path measure induced by this diffusion process. I'm going to try to select it so that it is as close as possible to the true time reversal. And if you do that, it turns out that you end up with a loss function that looks like score matching, okay, like a score matching loss function, on which using some kind of score matching trick can be reformulated as what I was presented in previous slide. So I don't want to spend too much time on this, but this is just to tell you that there's a kind of elegant continuous time formulation of this kind of mechanism that justify the terminology diffusion, on which can be useful when analyzing theoretically this type of algorithm. Okay. So now what can we say a bit theoretically about that? So I don't want to spend too much time on really the kind of mathematics behind this type of techniques, but let's say, so the result I'm going to present here is a reassuring result, which tell you that indeed, if you had a neural net approximation of the score, which provides some kind of reasonable approximation of the true score, then indeed the kind of generative model you build, okay? So you're going to have this kind of generative model, which is given by this kind of, approximate time reverse Markov chain, where you can exactly quantify, basically, you can quantify a bound between the distribution of the sample that are obtained by your generative model on the true distribution. and it can be upper bound essentially by a sum of two terms. One term is essentially the second term here on the right hand side is a term that is really which is related to the error you commit when you approximate the score term. Okay, and the first term is the term that is related to the mixing property of the Einstein-Uhlenbeck process you use to noise your data. Okay, so importantly, for those of you who are familiar with Markov chain Monte Carlo method, you might be a bit puzzled why one can simulate this kind of Markov chain in extremely high dimension, and yet not having any mixing issues. Well, this type of result shows you that indeed, remarkably, this kind of denoising diffusion model do not suffer from mixing problem. Okay, and you have actually dimension-free convergence rate for this kind of denoising diffusion model. So it's quite a remarkable result. This explains partly some of the success of this technique. Okay, it looks a bit like MCMC or like, you know, this kind of Langevin dynamic that people have worked a lot on recently in machine learning, where they have very different properties, and the properties of denoising diffusion model are essentially much better than the properties of standard Langevin dynamics. Okay, so that concludes some of the first part of this talk, which was to say we have this kind of really powerful class of techniques that have been developed in machine learning recently, which is really the idea that you add noise progressively, and you do it such that basically you add noise progressively, and you transform your sample in some kind of Gaussian noise sample, and then you try to reverse this dynamic. Okay. Now there's a problem with that. And one of the problems of this kind of techniques is that, well, you really need to add noise kind of sufficiently slowly so that basically you go slowly from a data sample to a noise sample. On each time you want to generate a sample, you need to go back from the Gaussian noise sample slowly back to the data sample, but it takes a long time. It's much more, in particular, computationally expensive than GANs. Okay, and the reason is because you would need to diffuse a long time forward, and as a result, because your generative model is simulating basically the same diffusion but in a backward direction, it will take you a long time as well. Okay, so those models can be computationally expensive. Okay, so here I give you an example in basically simple two-dimensional distribution, represented correspond to a S-shaped two-dimensional distribution. Assume you diffuse forward, but not long enough so that essentially at time n, in discrete time or time t in continuous time, your distribution looks nothing like some kind of Gaussian distribution, where even if you're able to basically perfectly approximate the score, if you start from a Gaussian distribution, you try to reverse that, at time 0, you have something that looks nothing like the distribution of the data. And the problem arises from the fact that basically the marginal distribution at time n of your diffuse data is nothing like a Gaussian. So that's a problem. Okay. So is there a way to speed up in a principal way denoising diffusion model? Okay. So what I'm going to do is I'm going to reformulate the kind of generative modeling problem as some kind of so-called Schrodinger bridge problem. Okay, so I'm gonna formulate what is a Schrodinger bridge problem. So I'm gonna consider a base process. The base process, what it is, well, is nothing but the joint distribution, you know, of my discrete Markov, the first discrete Markov chain I was considering. So you start from the distribution of the data, and you add noise progressively. Okay, so that define a joint distribution. Okay, and now I'm telling you what I'm interested in finding is finding a distribution on the same path space, okay? So distribution of x0, x1, x2, xn, which is minimize the curl between pi and p, okay? The feedback level divergence, subject to the marginal at time 0 of pi, which I denote pi naught. I want this marginal to be exactly distribution of the distribution of the data, and I want its marginal distribution at time n to be exactly equal to my Gaussian distribution. Okay, so I want to minimize the scale of the distribution pi, but the scale minimization problem is under two marginal constraints. I want the marginal distribution of pi at time 0 to be equal to p data, its marginal distribution at time n to be exactly Gaussian. Okay? Assume I find the solution to this problem. I call it pi star, the solution. Well, then I tell you the following thing. I could basically now use ancestral sampling on pi star. Okay? By construction, if I were to use ancestral sampling on pi star, I would obtain at time 0 a sample from p data, because basically by construction, the marginal distribution of pi star as 0 is the distribution of the data. Okay. And also, note here the important point is I never make the assumption that the marginal distribution of xn on the p, this kind of base process, is close to a Gaussian distribution. Okay, so if I could solve the solution to the Schrodinger bridge, I would not require basically having to diffuse long enough from the marginal distribution of xn on the p to be Gaussian. That's the key point. Okay, so that's the Schrodinger bridge problem. The question is, first, is it related to something we know? Is there a way also to compute it, or at least approximate the solution of Schrodinger bridge problem? So I'm not going to elaborate too much on the connection basically with optimal transport, but it's important to realize that essentially solving this kind of problem is equivalent to solve some kind of entropy regularized version of optimal transport between the distribution p data, the distribution of the data, on a Gaussian distribution. So you can think really that this Schrodinger bridge problem is just an entropy regularized version of optimal transport. Okay. Okay, so that's the first point. That's quite interesting. Now, question, how do you solve the Schrodinger bridge problem? Well, the Schrodinger bridge problem, it has a very long history in the maths literature, and there's been statistics, linear algebra, and so on. And there's an algorithm that was proposed as early as in 1940 that had been proposed to solve it, and that has been rediscovered many, many times in the literature, and is known as iterative proportional fitting. In machine learning, in the context where you're dealing with essentially atomic measure, this algorithm is also known as the Sinkhorn algorithm, and was basically promoted in machine learning by Marco Cuturi in a kind of landmark paper, Norris paper in 2013. But here, we're not dealing basically with such atomic measure. Think of measure distribution on RD, and this is where we're dealing with. Okay, so the algorithm solving the Schrodinger bridge problem is as follows. It's going to be some kind of iterated projection. So the original Schrodinger bridge problem, you want to minimize the scale distribution, and you have two constraints. Constraint that you want the marginal distribution at time 0 to be distribution of the data, on the marginal distribution at time n to be basically this Gaussian distribution PRF. Okay, so in the iterative proportional fitting recursion, you just ensure essentially one of these constraints at each iteration. So at the odd iteration, you ensure you minimize the curl subject to pi n equal to this Gaussian distribution. On that even iteration, you minimize the curl subject basically to the marginal time 0 to be equal to the distribution of the data. Okay, and you can show on the fairly mild regularity condition that basically this converge towards the solution of the Schrodinger equation. Okay. Now let's look a bit at essentially all these iterates of iteration proportional fitting, basically what they corresponds to. So if you want to look, you look at your iterative proportional fitting, you initialize it at the path measure pi naught, it is equal to p, the best process, okay? And you say, well, I want to solve basically first pi1, I want to compute pi1, okay? Well, it means that if I want to compute pi1, I have to minimize the curl between pi and pi naught, which is p, subject to pi n being equal to prf, okay? Well, by a simple decomposition of the curl, you can see that the solution to this problem admits some kind of explicit form. And the explicit form is as follows. What is pi1? Well, it's simply the distribution which admits basically as at marginal distribution at time n, this Gaussian distribution prf. And then basically what you have, you use, it's a backward, it's going to be defined somehow naturally in the backward direction. It used the kind of backward Markov transition kernel associated to the forward process P, okay? But if you look at that, well, this is what we are doing when we are doing the standard, essentially, score-based generative model. What we are doing is we are approximating this distribution. So the kind of like take-home message is that what we are doing currently, people doing currently when they do denoising diffusion model, well, you can think also alternatively as basically running the first iteration of iterative proportional fitting. Now, if it turns out that PRF was basically already approximately equal to essentially Pn, okay? If you had diffused according to P long enough that the marginal distribution at time was approximately normal, you don't have to do anything, actually. But if you're in a scenario really where Pn is quite significantly different from PRF, as illustrated in my graph in 2 dimensions, well, what IPF tells you is, doesn't matter, you just need to iterate the process. So what you do now is you're gonna do the next iteration of IPF. So you're gonna minimize the curl of basically between pi and pi1, constrained to having the marginal distribution at 0, which is given by the distribution of the data. Once more, basically, it corresponds, it has a kind of semi-explicit expression. And this expression is essentially some kind of forward process. It defines the distribution of a process which is naturally kind of evolved in the forward direction. So this is a process that starts from the distribution of the data. On this forward dynamic is obtained, this forward transition kernel are obtained by time reversing essentially the backward process pi1 defined in the previous iteration, okay? So that's really the way it works. So essentially what you keep on doing is you're going to define a sequence of forward and backward process. On each time to define them, you change the initial distribution and you time reverse the dynamic of the previous process. Okay, so that's the way it works. In continuous time, it has some kind of nice essentially expression in terms of diffusion. So really what you have is that at odd iteration, you have this kind of like backward diffusion that are initialized at the Gaussian distribution. On that even iteration, you have essentially some kind of forward diffusion, which are initialized at the distribution of data. And you have some kind of recursive expression between the drift of this diffusion, which involve the intractable score, which can be estimated using the same type of regression ideas that are presented beforehand. Okay, so that's really the kind of core idea behind this kind of Schrodinger bridge type techniques. Practically, what you're doing is very similar to what you're doing when you're doing this kind of standard denoising diffusion model. In the standard denoising diffusion model, you have to train essentially one network that learns all basically the score from time 0 to time n, but n has to be very large, okay? And then eventually, when you do simulation, you simulate some kind of long diffusion from time n to time 0, okay? When you're doing this kind of Schrodinger bridge, you have an algorithm where you're going to have to learn, you're going to do several iterations of your IPF. You're going to have to learn the score, essentially, of each of these forward and backward process, but you're going to have to learn them over a much shorter time horizon. And when it comes to generation time, you just need to essentially simulate some kind of backward diffusion of a short time horizon, okay? So although it might look more expensive, it is not actually in practice. Okay, so I'm sparing you the detail. Okay, so as an illustration, let's come back to my kind of like toyish example. So in 2 dimensions, remember, this is revisiting my 2 dimensional example, which was an example where the marginal distribution at time n under the initial forward diffusion was nothing like a Gaussian, so that when you were basically restarting from a Gaussian distribution and simulating backward till time 0, it would not generate like anything like the distribution of the data. But this thing corresponds also to the first iteration of this kind of iterative proportional fitting. So if you iterate the algorithm, that is, you start from the distribution of the data, you time reverse basically the process that I've generated previously, and you iterate, you end up eventually after a few iterations, you end up with a model that is able to generate in a few time steps, going from the Gaussian noise sample to the distribution of the data. Okay, and think of it, it's basically also an approximation of optimal transport, of the optimal transport between these 2 distributions. Okay, so this is the other example we have in the paper. I'm not going to spare you that. We have it also for images. So this thing were obtained about a year and a half ago. There are also other improvements which have been proposed in the denoising diffusion literature, but they some are orthogonal and complementary to what we are presenting here. Importantly, this thing is not limited to this kind of denoising generative modeling task, because there's no reason we should basically, we have to do some kind of transport, if you want, between the data distribution and the Gaussian distribution. So in particular, if you give me 2 empirical distributions, then basically I can use this kind of mechanism to interpolate essentially between these 2 distributions. And you can think as basically, once more, some kind of approximation of the optimal transport, of an optimal transport between these 2 distributions. So here, for example, we interpolate between the distribution of EM-NIST and M-NIST. Okay? Another thing you can do, for example, is that, say you've worked really hard, you have a GAN, which is actually already generated very good, very good images. You say, well, instead of kind of learning a new diffusion model that takes me from Gaussian noise sample to the distribution of the data, maybe what I could do is that basically I could have an algorithm that takes me from the GAN distribution, which is not exactly the distribution of the data, to the data distribution. And somehow what this algorithm would do is refining your GAN approximation to get closer to the distribution of the data. You can use this algorithm in this context, and it proved to be quite useful. Okay, so we don't have much time left, but I just want to explain also very briefly that this can be generalized so as to do conditional simulation, okay? So in particular, in a lot of scenarios, we are not interested really in doing just pure generative modeling, but we have some kind of additional conditioning information we would like to basically exploit so as to sample approximately from a resulting posterior distribution. On those techniques also generalize to this scenario. So it's a little bit complex. I don't know how many minutes I have left. Could you please tell me? Could you please tell me how many minutes I have left? Oh.
Sorry, you have 5 minutes?
Okay, 5 minutes. I go very quickly. Okay. So you might, if you are interested in generalizing this algorithm to scenarios so as to sample from a posterior distribution, well, that seems actually quite tricky. In particular, you know, could say, well, I could try to generalize the Schrodinger bridge approach that takes me from data distribution to this kind of Gaussian distribution and replace that by a Schrodinger bridge that takes me from the posterior distribution to the Gaussian distribution. But obviously, I couldn't apply the algorithm I've developed beforehand because this algorithm requires me to be able to sample from the data distribution, or here it would require me to sample from the posterior distribution, which is what I'm trying to achieve in the first place, okay? So is there a way to get around this problem? And it turned out there's a very actually simple way to get around it, which is essentially to kind of doing this kind of like a Schrodinger bridge of an extended space where now you work in the joint space of essentially, say, your image space on your further observation space. And then essentially you build some kind of Schrodinger bridge onto this kind of joint space, and that allows you to do conditional simulation. So we don't have much time to explain it, but what I want to say is that those ideas can be basically directly essentially extended to this conditional simulation framework. And it's really practically, it requires like 3 lines of code of modification, and you can do it. Okay. So I give you an example here. So this is an example where we use this kind of techniques for image super resolution. So this is really ground truth images. Okay. I assume I have access to this kind of degraded version of the observation. And literally what I'm interested in is I'm interested in basically obtaining potential sample of basically the original image given this corrupted observation. Okay. So you can do that using also a conditional version of denoising diffusion model, or we did it also with this kind of conditional version of Schrodinger bridge, which turned out to provide kind of much more actually better result as terms of FID and things like that. Okay. So maybe another illustration, say here, for example, is another example of super resolution. So this is the original image. This is the kind of degraded image I have. And here, this is basically our algorithm that generates at each iteration some sample from the posterior distribution. So we are in 100,000 dimensions. It's fairly high dimensional. And we see that it does actually things which are very sensible. So for example, here, where when you look at the corrupted version, this person might have glass or not. So sometime, you know, it's going to generate sample where someone has glass, sometime has not, and so on and so forth. It provides kind of fairly interesting results. So I basically recommend you to look at our paper if you're interested in this type of research. So just to finish, so there's a lot of interest in this kind of denoising diffusion model. We can show actually that theoretically, indeed, it's a principal class of techniques. It's possible to speed them up using ideas from optimal transport, namely using kind of the Schrodinger bridge type techniques. These techniques can be extended also so as to do conditional simulation, which is, I think, more important in practice. than unconditional simulation. And there's a lot of extension, you know, one can work on. So my group has in particular work in scenario has basically developed some kind of equivalent this denoising diffusion model on discrete space. We look at it also on Riemannian manifold for some application to protein generation. And there's a lot of it's a very exciting area where if you like, you know, a bit maths and you like to do like some cool things, you know, it's a really interesting and a lot of still a lot of open question. Okay. So I will just conclude with that. If you're interested in exploring this type of basically generative modeling idea, I've listed in the first two references here, I would say are the kind of two main references in the field, okay? One is by the group of Iterative in Berkeley, and here is by the group of Arnaud and the people at Google Brain in Stanford, okay? And here this is the variety of work my group has been doing, and in particular, these two first papers are basically present the idea to kind of how to speed up denoising diffusion model using Schrodinger pressure idea. That's it. Thank you.
Thank you for your nice talk. Let me take one or two questions.
Nice talk. I have some question. Rather than maybe using Gaussian, I see why you want to have Gaussian units. You're getting benefits. Everything is Gaussian. Is it possible to add another type of noise and maybe gain something out of that? I mean, I understand perfectly well why it's Gaussian, but
So,
I'm just saying, yeah, for some other purpose, is it possible to add a different kind of noise with and gain something? I mean, is that a possibility?
yeah, it's possible. So for example, we had this paper, the last paper listed here. So we work in discrete state space. And essentially what we do, we diffuse toward the uniform distribution on this discrete state space. What matters is not really that it's Gaussian, you know, that you had Gaussian noise, is the fact that you should be able to kind of reverse this kind of forward process that corrupt progressively your data. So as long as you have a forward process that goes towards, say, that diffuse toward the kind of simple distribution that is easy to sample, if you're able to approximate correctly the time reversal process, then you're good. You don't need to have this Gaussian thing yet.
Yes.
So on manifold, for example, the second paper here on manifold, on this we work on compact Riemannian manifold, and then there we diffuse toward the uniform distribution on the manifold.
So I think you covered with this method, you can interpolate between two images. You can also perform GAN type of conditional GAN type of generation, all of that.
Yep.
There isn't any.
Yeah, you generalize all the idea that we are for conditional GAN. Basically, you can that extends here as well.
Yeah, and there's no problem. There's no difficulty, and maybe yes.
I think compared to GAN, there's still the fact that it's a bit more costly. There's been a lot of progress to speed up those diffusion models. It's still a bit costly to run those algorithms compared to GAN, although there's been a lot of progress. So that may be the main, you know, their main drawback. The benefit compared to GAN is that it's much more stable to train because there's no it's not an adversarial problem. It's just literally a kind of simple loss, really. So there's not all the instability that you can face when you have GAN. Also, empirically, people found out there's much less like mode dropping issues than with GAN. So in this respect, it's quite good.
Thank you.
Okay, let me take one more question.
Thank you for your insightful talk. It's often, well, it can be the case that the data distribution has different supports, and if the supports are far apart, then diffusion type third model may only converge upon a single support and not the other different one. Have you considered this problem when you were viewing this kind of?
Sorry, I really cannot hear the sound is very poor, so I cannot hear you. I apologize actually. Can you?
Sorry,
The sound is very bad.
Data distribution, it has different supports. And those differences, they're very far apart. If they are very far apart, then can it be that only one of them is activated and the other one is kind of disregarded?
I'm sorry, I really cannot hear the sound. Okay, so it's written. I apologize. So yeah, I mean, I think there's not much issue with that because you can see that in a lot of this example, I mean, it's not like the data distribution is going to be kind of fairly multimodal, and it doesn't seem to be really that it's really struggling to do this. I mean, it's much less problematic than for GAN for sure. We have much less mod dropping issues than for GAN. I'm not saying there's none yet. There's some indication that when you have really kind of unusual observation, the model then memorize them. But otherwise, it's much less prone to this kind of mod dropping than GAN. That's for sure.
okay, it's time up. Let's thank the speaker. Okay. Thank you very much, Arnaud.
Thank you.
Okay. Bye.
Bye-bye. Thanks.
네, 이제부터 저기 광고가 있습니다.